quantitative analysis of growth. Now let's get into nucleation, and specifically the rate of nucleation. So we know that at lower temperatures, i.e. when delta T increases, when our undercooling, when our temperature decreases, we're going to have nucleation will be thermodynamically preferred. Again, why? Because this term, magnitude, decreases at lower temperatures, so we need to maximize our favorable enthalpic interactions, and we want to nucleate our lamella and our spherulites. So we can approximate the rate of nucleation with this equation right here. So in this term, our delta G, that delta G is just this term that we've been dealing with previously. So delta GV, and remember back all the way back as I go through my notes right now to get the actual value. All the way back from our notes, we had the delta GV times the volume, so x squared L, again for our lamella, plus our delta GS, where our delta GS is equal to this 2 sigma E x squared plus 4 sigma XL, but we know that L is much, much smaller than X, so this term gets canceled, and we found this relationship that our lamella spacing, basically this delta GV, x squared L equals 2 sigma E squared, these cancel, so L is a function of 2 sigma E over delta GV. Anyways, we plug in this expression here into here, and that is how, again, we see that this expression is proportional because we had also this relationship that delta GV equals, or is proportional to delta H, delta T, our undercooling over Tm. So as undercooling increases, again, as our temperature decreases, we are going to increase our rate of nucleation. So that kind of makes sense. So rate of nucleation increase as our temperature lowers. So again, the optimal crystallization rate will be some moderate, again, value. So again, near the melting temperature, likelihood of forming a nucleus, very, very small. So our crystallization rate is going to be very small, or our nucleation rate. So you kind of think, but it will also be our crystallization rate as well. So nucleation rate, very slow. Far below melting rate, our diffusion is very low. So spherulites, again, we're getting a little bit into our crystallization rate. So this is just for nucleation. For our nucleation, so our rate of nucleation is going to look like this. So as delta T increases, we're going to shoot up like that. Now, for our rate of crystallization, just like we talked about previously, we're going to want, so when we look as a function of delta T, we know that our, I'm going to call this is going to be my D term. So my diffusion drops off like this. My nucleation rate goes like this. So to maximize my crystallization rate, I need to have this moderate amount of undercooling. So again, at very, very low delta T, at high temperatures, what dominates? My diffusion. But there's basically no crystal, my diffusion dominates here. Let me do this. I should have done this right here. There we go. Hopefully that looks better. Anyways, you know what I'm talking about. So at low undercooling, high temperatures, diffusion dominates, but there's no crystals, or there's basically very, very few nuclei to grow. At high amounts of undercooling, my nucleation dominates because it's really cold, but there's basically no diffusion. So I need to find this Goldilocks moderate amount of undercooling in order to crystallize my material appreciably. So to maximize my crystallization rate. So again, my crystallization rate is maximized at some small amount of undercooling here. Now, these graphs are kind of very telling. Usually, when you look at this kind of crystallization rate graphs, so this delta T, there's usually some, what I call here, this delta T crit. So there's usually a critical amount of undercooling before you could even start kind of crystallizing, or your crystallization rate, crystallizing or nucleating your material. So this amount, the larger it is, it means it's the more difficult, like basically the more kind of amount of undercooling and energy that we have to put into our system. If that happens, if I have another curve like this, and this peak shifts, we kind of see something very similar, right? So here, my critical amount of undercooling is low, and I hit my maximum again, I don't have to cool my system down. I don't have to put in more energy in order to kind of crystallize or maximize my crystallization rate. So this can change depending on some parameters. So whether again, up here, this homogeneous and heterogeneous nucleation. So heterogeneous nucleation will have a lower delta T crit. So a lower amount of undercooling, again, because, again, if you look back at my ENGR 45 notes and some of the videos that we posted on nucleation and growth, heterogeneous nucleation, basically there's these kind of little defects or basically parts of your system where you could start to kind of nucleate. Usually it's at the edges where you can nucleate. There's some surfaces where it's favorable to start to nucleate your particles. So your energy barrier is lower for heterogeneous versus homogeneous, and thus you need less delta T, thermodynamic driving force, to start to nucleate. Similarly, depending on your polymer, as we're going to see in a bit, these curves can shift as well. So a polymer that's much more flexible and that is wiggly and basically has a lot of, it wants to maximize its conformational energy states, that you're going to have to put a lot more energy, i.e. more delta T crit, a larger amount of delta T crit than a polymer that is much more short, rigid, and that will want to basically fold. It'll be easier to kind of get those, to stack those particles, or a polymer that has much more favorable, and basically non-specific or specific enthalpic intermolecular interactions. So like H bonds or polar groups, et cetera, et cetera, et cetera. So yeah, that's basically it for crystallization rate. So as engineers, how are we going to modify, or how can we use this knowledge to modify our melting characteristics? So there's a lot of knobs that we have in order to change either our lamellar thickness or more importantly, our melting temperature. So one option is you could add branches. So what is adding branches going to do to the melting temperature of our polymer? Well, as we've kind of discussed in the previous lecture, if you add branches, typically this is going to lower the melting temperature. Same behavior as if you lower the molecular weight. Why? Lower molecular weight, more chain ends. So again, hard to incorporate these. They act as defects, as we kind of saw previously. You can modify the chemical structure of your backbone. So again, stiff polymers, easier to crystallize, especially if they have bulky groups along the main chain. Higher melting temperature, rotation is unfavorable. Flexible groups, especially silicon, will decrease your melting point. Why? Because they want to move and rotate around those backbones. So, and again, any group that participates in H bonding, electrostatic, will increase that melt. So again, if there's favorable and intermolecular enthalpic interactions, then you're going to increase your melting temperature. Side chains. Long flexible side chains decrease your melting temperature. If we have shorter bulky side chains, it will actually enhance elongation because it restricts rotation of the main chain, and that will increase your TN. And finally, environmental conditions. So if we apply temperature, if we increase temperature, obviously that is going to kind of change the conformational entropy component of your system. So it might be more difficult, as we saw, that as a function of undercooling, that changes essentially your crystallization rate. Applied stress and pressure is very interesting. So again, you could, if I have a polymer, a mixture, bath, and I apply some stress here, I'm going to elongate my chains. This is going to be easier to kind of stack, and that's going to increase my melting temperature. And it'll also increase my lamellar thickness as well. So we'll see this. I've created a nice little table. You can definitely expect I would have this on your sheet ready to go for an exam, because this is a good, again, a sanity check. There's lots of things, inverse relationships going on here. So this is a nice double check for you as you're kind of going through studying and approaching problems, and you can see, okay, how does undercooling affect my melting point? Well, it doesn't really, but it affects, again, higher undercooling. We saw that my critical lamellar thickness is going to decrease. Why? Because, again, that conformational entropy component is smaller, so I don't need as much undercooling in order to kind of stack my lamellar and fold my branches. Molar mass, increase my molar mass. You can see how that will, again, increase my molecular weight. Again, just because the number of interactions increase. Pressure, again, same thing as stress. And now you could also add branches, again, bulky groups, just what we've kind of looked at previously. So have this table ready to go. Use it for your P-sets, use it for your exam, and if you have any questions, let me know. I'll see you in the next video. Thanks. Bye.